Everyone, thanks for coming to our fifth geometry topology summer school. So we are running this research schools for a while. So this is the fifth one, and which is supposed to be a real meeting, but we have to turn it into online because of virus situations. So I hope you're going to enjoy it. We put few lectures for online lectures because scientific committee told us too many lectures is not going to be very good. So we're going to have approximately 3 lectures a day. So for the whole 2 weeks, and there is going to be some pre-recorded lectures as well with the live recordings. So afternoon. So that those I'm gonna broadcast them, so you're gonna see them. So welcome to everybody. So here is our first speaker today, Roger Nakad. He's gonna talk on species structures on manifolds and geometric applications. It's a very interesting subject in differential geometry. So I hope we're gonna enjoy it all together. All right. So if you want to also record the lectures, just let me know so that I can allow you access. All right. Thank you very much.
Thank you, Mustafa, for the introduction. First, let me ask you if it is possible to close the camera so we can have better connection.
Yeah, right. So, yeah, exactly. Yeah. So, all right.
Okay.
Yeah.
Okay, so thank you.
You asked me to close it also. It's gonna. Maybe I can close mine also. Maybe it's gonna make it better. Okay, yeah, just start then.
Okay, so thanks again for inviting me for this, to give this mini course on species structures, on manifolds, and geometric applications. So I'm going to be very elementary at the beginning, and please feel free to ask questions at any time. Just by making any voice you want or just asking me questions. So today in my first session in this mini course, I'm going to give you few applications of the topic. I'm going to introduce the topic and some motivation as well. And of course, at the beginning, I'm going to give few elementary results in linear algebra that I'm going to use later on. So for today, I'm going to divide my session into 2 parts. The first part, I will be motivating the species structures on manifold, the Dirac operator, etc. And in the next part of my session today, I'm going to introduce the Clifford algebra and the representations, something that I'm going to use later on tomorrow and after tomorrow in my upcoming sessions. So the first part for today will be a motivation and background. So I'm going to start, I think all of you are able to see my screen. Anyway, so we in the set of functions on Rn, all of us, we know how to define the Laplacian. We can define the Laplacian or the Laplace operator locally, or because I'm on Rn, it acts on function and it's given by sigma j from 1 to n partial derivatives of the sigma xj squared. And this is the Laplace operator. It's a second order operator, differential operator. And now the question is that possible, for example, to define a square root of the Laplacian? So my first question is, can we define the square root of the Laplacian? So what do I mean by the square root of the Laplacian? I mean a first order operator So can we define a first order differential operator? I'm going to call it D. I cannot call it the Dirac operator yet, but let's call it D, such that D squared is the Laplacian, or D is the square root of the Laplacian. So let's try to make the construction together. And normally, if I want to define a first order differential operator D, what do you think about it? I should put del xj here with some coefficient bj and try to sum from 1 to n. So, and now I will ask the question, what will be my bj? Maybe they will be functions on Rn, or functions or complex functions. So let's see. So if we if we give to our undergrad students this exercise, how it will be the form or the shape of bj such that d squared equal to Laplacian. So you get d squared equal Laplacian after calculation, of course. If you want, I can write it. So you will get d squared, so you will get sigma bi bj plus bj bi del xj del xi plus sigma bj squared del xj equals the Laplacian minus sigma del squared del xj. And of course, if you would like to identify between d squared and the Laplacian, automatically you should get that bj bi bj plus bj bi should be equal to 0 for any I different than j, and you should get that bi squared equal to -1. So in total, that's what we call the Clifford identities or property. Bi bj plus bj bi for I different than j should be 0, and bj squared or bi squared should be equal -1. And as you can see, of course, if you let bj be complex function, this is not possible due to the first one, the anti-commutative relation. And if you would like to let bj be real function, this is also not possible, because real function squared cannot be equal to -1. But here we are. And so what we are going to do, so bj cannot be complex functions and bj cannot be real functions. So the goal is to let bj live in a space bigger than the set of complex functions or the set of real functions. So what is the easiest choice, or what is the normal candidate, is that we let bj live in the set of matrices, and or if you want, we let bj be matrices. Why? Because we know that bj, if you have a matrix, its squared could be -1 or minus identity, and because bj bk plus bk bj could be 0, as you know, the matrices cannot commute in general. So what will be our bj? I'm going to take example here. So let's start with
Roger, can you show the previous slide again, because it's somehow frizzy. Yeah, people want to see it. Okay, so you have coefficients for the partial operators and bi's. Yeah. Okay. Yeah. Right.
it's clear.
Yeah. Now we can see it. Yeah. Okay. So
of course, due to this relation in yellow, it's clear that you cannot expect to have complex functions or real functions.
okay.
So we would like to let
so
J live in space bigger. Yes, tell me.
Okay. I see. So you need these relations.
To be satisfied.
Okay.
Otherwise, you cannot take the square root of the Laplacian, or you cannot
Okay.
define the square root, which is d, that I cannot call yet the Dirac operator.
I see. Okay. Okay. And later on, you're gonna change your space of BIs to be a bigger space. All right. Thank you.
Yes. Which will be the set of matrices. You will see,
Okay.
Mustafa. Let's take example, Mustafa.
Okay. Yeah. You can continue. Yeah. Thank you.
Yes. If you live on R instead of Rn, let's take the easiest example. So your D will be I del x. Of course, this I here, it's clearly I squared is -1. So the second relation is satisfied. And no, and for the first relation, you only have one coefficient here, B1. So the first, there is nothing related to the first condition. So this is my B1 here. Go to R2, for example, and you expect to have B1 del x plus B2 del y, or del x2 as you wish. Now, if you take this matrix I0, 0, I, let's call it this one B1, and this is what we call the Pauli matrices, 0, I0, call it B2. And now, Mustafa, as you can see on the special case R squared, now I'm going to put it on Rn, it's easy to check that B1 squared is -1, I mean minus identity, B2 is also -1, and if you make B1, B2 plus B2, B1, you will get 0. Okay, and that's what we call the Pauli matrices. And now I can define this D in the following way, and this D will be the square root of the Laplacian. Let's go to R3. So normally you should have D equal B1 del x plus B2 del y plus B3 del z. So I'm going to consider the same B1 as on R2. So 0, I, 0, 0, I. For this, for B2 to be 0, I, 0. And for the third one, B3, it will be minus I, 0, 0, I. So again, this is B1, this is B2, and this is B3. And anyone can check that B1 squared is equal to B2 squared equal to B3 squared equal to minus identity, and B1, B2 plus B2, B1 is 0, or B2, B3 plus B3, B2 is equal to 0. So all the both conditions are satisfied in my case, and you can do it for R4, for R6, for R7, etc. until Rn. So I was able to define, not me, of course, that's what the work of Pauli and Dirac, this is what we call the Pauli matrices. So you were able to define the D, which is a first order differential operator, whose squared, if you take the square of D, you are going to get the Laplacian. That's what we call the square root of the Laplacian. But of course, I need to always keep in mind that I'm working on Rn. Things will get will be different, at least when we go to an ambient manifold. So, or like on the sphere, or on the torus, or any other manifold. So I'm still working now on my simple example Rn. So if I want to go more general, instead of R, R2, and R3, on our end, D will act on psi, these special functions, which are functions from Rn to C to the integer part of n over 2. Let's come back to the previous slide on R, or the previous one. On R2, for example, here, the D will act on functions which go from R2 to C2. And on R3, the D will act again on functions that go from R3 to C2 as well. So that's why you can see here the integer part of n over 2. So on R2, it acts on function from R2 to C2. And on R3, for example, it acts also on function from R3 also to C2, and etc. So when you move to R4 and R6, you have different type of function. In this case, we will call this is what we call the Dirac operator. That's what we call the Dirac operator. These special functions here are called the spinor fields, or two simple spinors. So what is a spinor for on Rn? It's a special functions from Rn to C2 integer part of n over 2 where the Dirac operator acts. And in this case, you can say that Rn is a spin manifold. So roughly, what does it mean, a spin manifold? So it's a manifold, or Rn, it's a manifold where you can define the square root of the Laplacian. Of course, you cannot define all the time the square root of the Laplacian due to these two Clifford identification, bj squared equal -1, blah, blah, blah. But on Rn, you can do it easily by going to matrices. That's why we say that Rn is a spin manifold. Psi will be called spinor field. D will be called Dirac operator, and this particular or the special space here, C2 integer part of n over 2, will be called the spinor bundle. So I'm just giving now all the ingredient for spin or spin C geometry, and as you know all now, if I want to go from something local to something much more global, I mean from Rn to any other manifold, you can imagine now what will be the spinor fields. The spinor field, I'm going to explain it later on. The spinor field will be a vector bundle whose fibers are C2 integer part of n over 2. And what does mean a spin manifold? It's a manifold where we can define the square root of the Laplacian. So hope that this part is clear. I'm just now defining the Dirac operator only on Rn. And I'm trying to explain how later on we will be able to generalize it to any manifold of dimension n, any Riemannian manifold. So again, I need later on to be able to define a spinor, the Dirac operator. I need a vector bundle that I'm going to call the spinor bundle, as you can see it here. And what will be this vector bundle? The fibers of this vector bundle at a specific point x will be C2 integer part of n over 2. And in this case, I will call my manifold to be a spin manifold. So that's the Dirac operator on Rn. My screen is again here. I don't know what's happening due to connection, maybe. Okay, great. We are back. Okay, and now why we are interested in studying the Dirac operator and spinors. So we have, first of all, this is one of the big theory on, for studying the Dirac operator and spinor is the Seiberg-Witten theory, which is based on four-dimensional manifolds, and which say that every four-dimensional manifold has a spin C structures, or for the moment a spin structure.
Okay, seems yeah. Okay.
So you can see my screen again, right?
Yeah, great, great. Yeah,
Okay.
what did you do? I mean, did you?
I don't know. If that's a connection problem. It was disconnected. That's it.
Okay, okay. Yeah. Hopefully we didn't have to start all over again. Okay. Oh yeah, just continue. Thank you.
So application of the Dirac operator is not only of the Seiberg-Witten theory, but also the twistor theory. Twistor theory, yeah. Also in the Yamabe problem, and many other applications like surfaces theory, submanifold theory as well, supersymmetry, supergravity, superstring theory. But in my mini course, I'm going to focus on one point, which are the geometric Okay.
Oh, yeah. Okay.
So I'm really sorry again. So
Take your time. No
the
problem.
goal the, the goal of this mini course is to focus on one application, which is the geometric, uh, some geometric application. I mean geometric application on submanifolds. So, for example, we will try to prove a Lawson type correspondence between minimal surface and surfaces of constant mean curvature on R3 or on the sphere. So, I, so in all my mini course, my point is to study the geometry of submanifolds or surfaces in particular, and using spinor fields and maybe using special spinor fields. And I'm not going to focus on the other applications which I have mentioned, like Witten theory, twisted theory, Yamabe problem, and etc. So to also motivate this point of why we would like to study the geometry of submanifolds using spinors and using the Dirac operator or spin and spin seek geometry, I'm going to start by a simple result of Lishnerovitz. Lishnerovitz in 1963 proved that if you have a manifold, a Riemannian manifold, which is a spin manifold, so for the time being, since I didn't go in details, by a spin manifold, just keep in mind that a manifold where I can define the square root of the Laplacian. So I can define the Dirac operator. Just take it locally on an open set U. So you have Rn if you want, and then you can define the Dirac operator. For example, Lishnerovitz proved that the first eigenvalue of the Dirac operator is strictly bigger than 1 over 4 the infimum of the scalar curvature of the manifold. Of course, here I'm assuming that the manifold is a spin with positive scalar curvature, strictly positive scalar curvature. So he proved that the first eigenvalue squared is bigger strictly than the 1 over 4, the infimum of the Dirac operator. And then by applying the Atiyah-Singer theorem, um, he got geometric results. For example, that the space of harmonic spinor, the kernel of the Dirac operator, is trivial in this case. And another, for example, Ijazi in Usama Ijazi in 1985 improved this inequality and proved that the first eigenvalue of the Dirac operator is bigger or equal, sorry, not Ijazi, Friedrich. I'm sorry. Thomas Friedrich proved in 85 that it's bigger or equal than n over 4 n minus 1, the infimum of the scalar curvature. Of course, here equality case can be attained. We can obtain the equality case, and the equality case is characterized by having a special spinor field that I'm going to define later on. It's called a spinor field, a killing spinor field, and the spinor field, the killing spinor field, characterizes the sphere in some dimension, and it characterizes also other space than the sphere in some other dimensions. And this is from an intrinsic point of view. From an extrinsic point of view, also, Friedrich in 1998, for example, proved that if you would like to immerse a surface into R3, it's enough to have a spin. Of course, you have to have M spin with the Dirac equation. So what is the Dirac equation? So you have a spinor field plus phi, I'm going to call it phi, that satisfy d phi equal h phi, where h is the mean curvature of the immersion. So in order to immerse a surface in R3, it's enough to have the Dirac equation, and vice versa. If you have the Dirac equation, then on your surface on a manifold M2, you are sure that you can immerse it into R3 with mean curvature H. So that's some results that can motivate the use of spin geometry on the intrinsic and the extrinsic point of view. Now in 1994, we moved from spin to spin C geometry because of the equation of Seiberg-Witten theory, which the theory again is based on four-dimensional manifold, and it says that every four-dimensional manifold has a spin C structures. And of course, as you know, from the theory derived the work of Donaldson on 1982. And so the results of Donaldson were direct result from the Seiberg-Witten theory on the four-dimensional manifold. Of course, why are we want to move from spin to spin C geometry, or from spin to spin C manifolds? Almost all manifolds that I know, at least that's what I know, are spin C. For example, every spin manifold is already spin C. I'm going to define spin C. Now, spin C means that locally you can, of course, define the Dirac operator, but you have also some other constraint on a vector bundle, on the complex line bundle. So every spin manifold is spin C. Every complex manifold is spin C. Every Kähler manifold is spin C. Every Sasaki manifold is spin C. Some CR manifolds are spin C. So that's what I'm saying. From what I know, almost all manifolds are spin C. So they have a natural spin C structure. So you can define in a very natural way the Dirac operator on the spin C manifold. Some result on this direction of the spin C manifold. For example, Ijazi, Montiel, and Urbano in 2006, they proved that if you have a Kähler manifold, and you have a Lagrangian submanifold, by restricting special spinor fields here on the Kähler manifold, what we call the Kählerian killing spinors, to some Lagrangian submanifold, you can get geometric information, you can get geometric and topological information, like some results on the Betti numbers on the Lagrangian manifold. Okay, so these are some recent results on the use of spin and spin C geometry on the study of submanifolds and surfaces. Many other recent results, like a characterization of the sphere, the manifold with boundary, and etc. But I'm not going to talk about them in detail, because I'm going to immediately start with my second part, which is I'm going to give a brief introduction or brief algebraic facts about the Clifford algebra before being able to define the Dirac operator or spin and spin C structures on a given manifold. So that's for my first part about just motivation, where we are going, and what I'm willing to do during this week. So the second part, algebraic facts.
If you want, you can give a break in the middle if you want. So just let you know about it.
Okay, so I can give break anytime you want. I don't mind.
Yeah, that's up to you. I mean, if this freezing thing happens, then we can give a break maybe something like that.
Okay, if you want, we can. If you want to take the break now, I don't mind.
Yeah, just continue. I mean, it seems like
Okay.
we just started. Yeah, okay. Yeah.
Okay. So I'm going to give you some algebraic facts about the Clifford algebra. So I'm going to denote, we denote CLN, the Clifford algebra. So what is the Clifford algebra? It is the unitary algebra generated by elements V and W in Rn, such that V dot W plus W dot V is minus 2, the scalar product with V and W. Here by the scalar product, of course, I mean the scalar product on Rn, and V and W are any elements in Rn, and the dot here is a binary operator that that I use to define my algebra or the Clifford algebra. Again, and the scalar product here is a canonical scalar product on Rn. More specifically, and as you can see, I will always refer to my introduction. I'm just, if you remember this relation, B1, B2, or Bj, Bk plus Bk, Bj, if J and K are different, it should be 0, right? So we are this is what we call the Clifford identification or the Clifford property. More specifically, if in terms of basis, if you have E1, E2, En, orthonormal basis of Rn. So what is my Clifford algebra? Then the set, it's unitary algebra, so I have the 1. Then EI1 dot or Clifford multiplication with EI2, etc. Clifford multiplication with EIK, where you let I1 and I2 and IK move between 1 and n, and K between 0 and n. Okay, so the following set is a basis of CLN, my Clifford algebra. So here I'm going to recall the dots here are the Clifford multiplication, AI1, AI2, AIK, where you let IK move strictly between 1 and n. For any k between 0 and n, automatically, guys, you can see that if it's a basis of CLN, then the dimension, the real dimension of CLN is of course 2 to the power n. Okay, so and I'm going, this is a real Clifford algebra. This is definition of the real Clifford algebra. And now what is the complex Clifford algebra that I'm going to denote it by CLN? It's nothing than the complexification of the real Clifford algebra. So this is a complex Clifford algebra. So this is a complex Clifford algebra. Maybe these definitions of real and complex Clifford algebra are a bit abstract. So let me give you some example. If I take, for example, CL1, the real Clifford algebra CL1. So a basis of CL1 is given by 1 and E1, and that's it. Of course, you can see that E1 E1 dot E1 plus E1 dot E1 should be minus 2, the scalar product between E1 and E1. So as you can see, I'm going to get that E1 squared is minus 1. And so this means that my E1 will be I. And so CL1, a basis of CL1, will be 1 and I, and so my real Clifford algebra CL1 is nothing but the complex plane, or C. So the Clifford algebra CL1 is C, and of course, if you would like to know the complexification of CL1 or the complex Clifford algebra, it's C tensor product with C, of course, which is the direct sum C plus C. So that's the first trivial example, if you want, or standard example. It's what is CL1. If you move and you would like to know a basis, or what is CL2, the Clifford algebra CL2, a basis of CL2 is given by 1, and then you have E1, E2, and at the end you have also E1 Clifford E2. So of course, if you check the relation of that define my binary operator, my binary operation, I mean UV plus VU is -2, the scalar product of UV, automatically you will have E1 squared is -1, E2 squared is -1, and of course, E1, E2 squared is again -1. And you can also say that, or you can see that E1 scalar E2, or Clifford multiplication with E2, is minus E2 E1. Okay, so of course here you can, or as people liking geometry, they can see that these relations are satisfied by H, the quaternion, and so we can say that CL2 is nothing than that the H, the set of quaternion. And of course, if you would like to take the complexification of, or the complex Clifford algebra, is the tensor product of H with R, the quaternion with C, sorry. And of course, we know that the quaternion tensor product with C is the set of matrices, complex matrices of size 2 by 2, C2, the set of complex matrices of size 2 by 2. So these are these two examples of what is CL1 and what is CL2, the real Clifford algebra and the complex Clifford algebra. Of course, we can deal with CL3, CL4, etc. I'm not going to give all details, but we have a complete classification of the Clifford algebra, the complex Clifford algebra, and the real Clifford algebra that I'm going to explain in my next proposition, especially for the complex Clifford algebra. Okay, that's the first example. Any questions that you have, or I can proceed? Okay.
Looks good.
Okay, great. So now I will come back to Rn, and keep in mind that I'm considering all the time E1, E2, En a basis of Rn, and automatically I have a basis of the real Clifford algebra given by the Clifford multiplication, and of course I'm defining the complexification of it, which is the complex Clifford algebra. I'm going to define the complex volume element. That's what we call the complex volume element. So this is E1, Clifford multiplication with E2, Clifford multiplication with E3, etc. Clifford multiplication with En. So I'm taking all the element of the basis of Rn, and I'm just considering all the Clifford multiplication of all of them up to the coefficient, up to a constant, which is I to the power, the integer part of n plus 1 over 2. So I'm going to use, or to use this complex volume element in my next result. Okay, so let's see. Okay, I don't know again. Okay, great. So that's what we call the complex volume elements. Now I'm going to talk a bit about the complex representation a theory of representation of the Clifford algebra, and in particular of the complex Clifford algebra. A complex representation, so the first result that a complex representation, okay, so a complex representation of CLN, of the complex Clifford algebra, is irreducible if and only if it is of complex dimension to the integer part of n over 2. Of course, guys, I'm not going to prove this linear algebra, this result. But I'm not going to prove this fact. It's well known that the complex representation of the complex Clifford algebra is irreducible. I believe all of us know what does it mean. A representation is irreducible if and only if it is of complex dimension to integer part of n over 2. More precisely, what do I mean by this? More precisely, so let's explain it. More precisely, if I'm going to split my explanation into two parts. If n is even, so if n is 2n, so the complex Clifford algebra, we know that has a unique, irreducible representation of complex dimension 2n. That I'm going to write it explicitly. I'm going to write it gamma to m. So it's a representation of CL2m or CLN, but n here is 2m, of complex dimension 2m, which is 2 integer part of n over 2 here, but n is 2m, so okay. So to the endomorphism, the complex endomorphism of C to m. And of course, this is, they are isometric. That's for in the case, in the even case. And if n is odd, so if n is 2m plus 1, then CLN, the complex Clifford algebra, has two inequivalent irreducible representation. So it has two irreducible representations that they are not equivalent, both of complex dimension 2m. More precisely, if I want to write it as I did in the even case, if I want to write it explicitly, I'm going to denote, because I have two, I'm going to denote the first one by gamma 2m plus 1, and the second one by gamma prime 2m plus 1. And so it's a complex representation of CL2m plus 1 onto the endomorphism of C2m. Great. And of course, these two representations are not equivalent. And so now I can tell you also the complete classification of the complex Clifford algebra. If I come back to my previous slide, so because it is isometric, I can say that CL2m is isometric to the endomorphism of C2m. So in the even case, I can write CL2m, it's nothing than the endomorphism of C to M, and of course you know it, this is the set of matrices, of square matrices of size 2m. And in the odd case, CL2m plus 1, Of course, this is not an they are not isometric here, of course. However, I can write it, it's isometric to a double copy of C to M, direct sum of C to N. Of course, it's clear now. The first copy is for the first irreducible representation, and the second copy is for the second, for gamma prime, the second representation, irreducible representation. And of course, these two representations are not equivalent. So now, if I come back to the two examples of that I gave, CL1 and CL2, you can get them from these classification here. So CL2M is the set of matrices C2M of size 2M, and CL2M plus 1 is a double copy of the set of matrices of size 2M. One remark before we move, in the even case, if I take gamma 2M in the even case, and I take the complex volume element, and you try to square it, you will get identity. And in the odd case, gamma 2m plus 1, you take gamma c, you will get the identity. However, if you take gamma prime, the second irreducible representation, which is not equivalent to gamma of the complex volume element, you are going to get minus identity. So that's for the odd case. And this first one is for the even case. This will be for grateful use later on to define a spin or spin C structures on a given manifold. And now I'm going to
Roger, what about the trivial one-dimensional representation?
Sorry?
You have the trivial one-dimensional representation, right? By identity.
Yeah.
And you told us that if the dimension is 2 to the m, it's automatically irreducible. Can it be? Yeah.
No.
Yeah.
No.
Here, yeah,
No.
exactly.
Yes. What I said here.
Is a unique.
Yes. Okay. Okay. So CLN has many representation, of course, but it has only one reducible representation of complex dimension 2m to 2 integral part. It has a unique reducible one.
Okay. Oh, not the converse. Okay, I see. Thank you.
Okay. And this is for the even case. For the odd case, it has two reducible representations of both of complex dimension 2m, but of course they are not equivalent.
Okay, thank you.
So, okay, so still in what to say in the algebraic facts that I'm going to use later on, and allow me to denote by CLN 0 is the even part of the complex Clifford algebra. So what is the even part? It's a subalgebra of CLN generated by, so what is the even part of CLN? It's like CLN, it's a subalgebra, of course, it's a part of the CLN. It's also generated by 1 and EI1, Clifford, EI2, Clifford, etc., EIK, but here you let I1, IK, etc. move between 0 and n, and also you let K place between 0 and n, but with the only restriction here that please choose your K to be even only. So this is the main difference between defining CLN and CLN0, and that's why we say that CLN0 is the even part of CLN. So we consider the Clifford multiplication between the elements, but only even number of elements. Okay, so that is the CLN0, the even part of CLN. It's like considering the half of the algebra. Roughly, it's like considering the half of the algebra where you take the Clifford multiplication only with an even number of elements. Okay, and my result here, my lemma, is that if you take the complex Clifford algebra now of dimension n+1, and you take its even part, you are going to get the Clifford algebra, the whole Clifford algebra of CLN, not CLN+1. So the even part of the complex Clifford algebra of dimension of the of dimension 2 the power n+1, two integer part of n+1, is the Clifford algebra, the complex Clifford algebra of rank n or of dimension 2n. So the dimension here is 2n, and here the dimension is 2 n+1, of course. But as I said, when you take the even part, you are considering the half of the elements roughly. So it's like dividing by 2 here, and then you get 2n, 2n. So both have the same dimension, of course, otherwise they cannot be isometric as algebras or as vector spaces. So, okay. So back again. So both as vector spaces have, of course, the same dimension. And the even part of the complex Clifford algebra, I'm going to call it of rank n+1 or of dimension 2n+1, is isometric to the complex Clifford algebra of complex dimension 2n. I'm not going to prove it here. I'm just interested in the result for later on. But if you want, I can give roughly or quickly the proof of this lemma y, and that you can just, guys, imagine if you take, for example, E1, E2, En with mu, a basis of Rn+1, and then take such that E1, E2, En is a basis of Rn, and consider the following map: CLN, CLN+1, the even part. So give me an element in CLN. So you give me an element in CLN, it is of the form EI1, Clifford, EI2, Clifford, etc., EIK, which gives me, it should give me something in CLN+1, 0. So here I'm going to take two cases, depending on the K here. If K is even, and because I would like to have an element in CLN+1, 0, I'm going to consider the same elements, EI1, Clifford, EI2, Clifford, EIK, and this does the job because K is even, and I would like to have a Clifford multiplication of even elements to get an element in CLN+1, 0. However, if K is odd, if K is odd, so this cannot do the job. I have EI1, Clifford, EI2, Clifford, EIK. This is the Clifford multiplication of odd numbers. However, how can I make it even and in n+1? Just take one more time the Clifford multiplication with the mu, the last vector in our n+1. It's easy to check or to prove that this is that they are isometric, or CLN is nothing than, or isometric to the even part of CLN+1, 0. So just this is a quick idea of the proof. You can check that the following map is in fact an isomorphism. Okay, and now I'm going to finish my algebraic facts with the last proposition, and that's what I also need for later on. So just remember gamma 2m+1. So gamma 2m+1 is one of the irreducible representation of the complex Clifford algebra in the odd case. Okay, so you have another one which is not equivalent to it, the gamma prime. But let's forget about it and take then only one, gamma 2m+1. And then if you take gamma 2m+1 of the even parts of 2m+1, you will get the automorphism of C to M. Now, if you take gamma 2m in the even case of Cl2m, the even part of Cl2m, you are going to get the automorphism of C2m plus, no, let me write it differently. You are going to get the automorphism of sigma 2m plus direct sum with the automorphism of sigma 2m minus. Before explaining what is the sigma 2m plus and what is the sigma 2m minus, so allow me to put it here as well. C2m is sigma 2m. So let's now, before proving this proposition, let's try to understand it well and then explain it later on. So if I'm taking gamma 2m plus 1 in the odd case of the even part of Cl2m plus 1, I'm going to get all the automorphism of C2m, which is, I'm going to note it sigma 2m, just as notation. And if I'm in the even case, gamma 2m of Cl2m, the even part, I'm going to get a double copy, sigma 2m plus and sigma 2m minus. From where does it come, sigma 2m plus and sigma 2m minus? Don't forget that in a previous remark, I told you that gamma 2m of the complex volume element squared was, I'm going to come back, was identity. Okay, and because it's identity, so I can split. My sigma 2m into two parts, sigma 2m plus and sigma 2m minus. So sigma 2m will be sigma 2m plus and sigma 2m minus, or the direct sum if you want, where it depends on the action of the complex volume element, where sigma 2m plus is the set of elements in sigma 2m, where the complex volume element acts as identity plus, and what is sigma 2m minus is the set of sigma in sigma 2m, of course, where the action of the complex volume element is minus identity. So the square of the action of the complex volume element squared is identity, which gives the following splitting of the sigma 2m into sigma 2m plus and sigma 2m minus, where sigma 2m plus, when the action of the complex volume element is the plus identity, and sigma 2m minus is the complex volume element when it acts as minus identity. Don't forget here in the first slide that sigma 2m by definition is nothing but c to the power 2 the power m. Okay, so that's that I'm going to use later on for the exact definition of spin C structures and spin structure on my manifold. If you want, I can give you a brief proof of the following proposition, at least for the first one in the odd case, and in a similar way you can get the even case. So I'm going to prove it. Let's take the odd case for n equal to n plus 1. Okay, so I'm going to consider gamma 2m plus 1, one of the irreducible representation, and which is in Cl2 m plus 1 normally into the endomorphism of sigma 2m. So sigma 2m denotes c to the power 2 to the power m. But now, instead of considering this irreducible representation, I'm going to restrict this presentation to Cl2 m plus 1, the subalgebra 0 here, and it defines, and as you know, we have seen in a previous lemma that the even part of Cl2m plus 1, 0 is isomorphic to Cl2m. So in total, this gamma 2m plus 1 restricted to the even part of Cl2m plus 1 define a complex representation of Cl2m of complex dimension 2m. But we know what Mustafa asked me about, but we know that there is only a unique reducible representation of Cl2m of complex dimension 2m. So they should be isomorphic. So from the previous proposition or results, we know that we only have a unique reducible representation of Cl2m of complex dimension 2m. But here I'm constructing a new one using gamma 2m plus 1. This means that gamma 2m is isomorphic or equivalent to gamma 2m plus 1 when you restrict it to Cl2m plus 1, 0. This means that you are going to get the first results announced in my proposition. And for the even case, similar for the even case. For the even case, just imagine I'm going to do similar proof. Just maybe you can imagine, if you are following me, you can imagine that you should do the same. But how to do the same? Instead of starting with gamma 2m plus 1 restricted to, you are going to start by gamma 2m restricted to Cl2m. But then you will get a complex representation of Cl2m plus 1. But we know that we have two complex irreducible representation, but they are not equivalent. This is why we get a splitting into sigma 2m plus and sigma 2m minus. The first one equivalent to the first irreducible representation, and the second one for the second irreducible representation, which are not equivalent. Okay, so that's all what I have for my algebraic facts. That's all the algebraic facts that I'm going to need later for tomorrow. And tomorrow I can immediately attack and the definition. What does it mean a spin-C structure? What does it mean a spin structure, and how we can define how we can define globally the Dirac operator. And then it's true that you have the Dirac operator square equal to the Laplacian. Of course, on our end, we saw that it's yes, the answer is yes. But just imagine when we go to manifolds, I have to add some curvature term because the curvature of Rn is 0. So I'm going to get a new formula for the square of the Dirac operator, d squared equal Laplacian plus another curvature term of order 0. All these ingredients will be explained and proved maybe tomorrow. So I'm going to stop here for today about the algebraic facts. Again, that's all I need for tomorrow. Normally people doing spinorial geometry or spin geometry, they are asking why I didn't define the spin group, the spin-C group, and the action, etc. I really don't need them actually if I would like to define spin structure from a geometric point of view. It's enough to have the Clifford algebra in the even and the odd case, as well as the reducible representation. So I'm going, Mustafa, to stop here. I'm going to stop sharing. I'm going to open my camera.